Welcome to Conceptual Physics, Chapter 10, Paul Hewitt's Conceptual Physics, Chapter 10, on center of gravity, or sometimes we say center of mass. So the center of gravity or center of mass, which are the same thing, by the way, sometimes you'll see us abbreviating it, calling it CM or CG. It's the same thing. So the center of mass, or the center of gravity, is basically if you take an object and you could average like where all the mass is, all the stuff, and find the point, the average of all the distance from the center. So for example, it's pretty easy to do this with a ball. You take a ball and you say, okay, where all the mass is, it's going to be right at the center of a ball. In a can, it's probably going to be, we can actually measure, it's probably right in the center of that can, but right, like if I poked something straight through the axis of the can here, and I poked it straight through the middle of the can this way, it's where those two wires cross, right in the center of the can is the center of mass. If I take another object is like a cone. If you can imagine a cone, okay, so let's say it's a solid cone. The center of mass, when you average out where all the mass is and average, it'll probably be somewhere like right here. Okay, in a can, you'll see it'll be right here in the center. Okay, if you measure, it'll be right here in the center. If you imagine we draw a line, it's right there in the middle. I'm gonna make it red, it's easier to see. With symmetrical objects, it's usually not too hard to find the center of mass. If I have a ball, a sphere, that's pretty easy, it's right in the center, because we're averaging where all the mass is right in the center. Okay, so what about a pencil? Okay, we've got a pencil here. It's going to probably be, sometimes we call this the balance point, the center of mass. And this is a really important thing with swords. Jenny, can you go get the master sword?
Okay.
This is a really important thing in swords, and we will get more to that later. But the center of mass is often we call the balance point. So here, like this pencil here, I'm going to say, okay, the center of mass is probably right near the center. Having a really hard time. This was never my strong suit. So you see here, center mass is probably about right. See how I balanced that there? It's balancing on my finger because I've got about equal, half of the mass is on one side, half of the mass on the other side. So here we've got a sword. Balance points are very important in swords. Usually they say a well-balanced sword has its center of mass somewhere around here.
I don't think it's supposed to be. It looks like it got bent.
All right, so the center, so here I didn't quite, okay, whoa, careful.
Be careful with that.
Be careful. Okay, so here the center of mass for the sword is right about here. With swords, they usually want the center of mass to just be like a few inches above the hilt. Because when you're fighting, if you've got a sword that's the center of mass is like way out here on a sword, like you've got this really long blade, and the center of mass is too far out, it's harder to wield that sword. And if the center of mass is too close to the hilt, well, then you've got this giant, it usually means you've got this giant hilt in the background that banging into you. The center, so when they talk about when people buy swords and they say, is it well balanced? They're talking about where is that center of mass?
Yeah.
There's actually a very specific place they want it. You could probably look it up. There's a formula and they tell you exactly for the best well-balanced sword, you want that center of mass somewhere along here. So it balances when the amount of hilt and whatnot that I've got on this side is equal to the amount of mass, stuff, atoms on this side to the atoms on this side. So when I balance this, here, can you get me some spoons and forks? When you balance anything, you're finding that center of mass, or where's that line I draw, that the amount of atoms on one side of that object is the same as the amount of atoms on that side of the object. So, if you see those videos where people are balancing rocks, that's what they're doing, is they're balancing. So here with a spoon, we can guess, okay, the center of mass is going to be closer to this side because there's more stuff on this side. Okay, so here, yeah, it balanced there. Why? Because the spoon part is bigger. Now, compared to this little flimsy fork, you can see the spoon, there's more stuff in the spoon part than I think there is in this fork part. So with this fork, I don't think it's going to be quite so close. See? If I do it this way, it tips down. If I put too close where I had it with the spoon, it'll tip down. Why? Because there's more stuff. Like this, there isn't as much stuff here, so that means I need to get it equal. I need to move my finger over here. Okay, now, do you see that? Do you see how the balance point for that fork, because the tines of the fork aren't as massive as the big soup spoon, it's further toward the center. Okay, you can take the master sword out. Do you see the difference between that spoon and that fork? Do you see here in this one, I had to move the center of mass is more toward the center here. With the spoon, the center of mass is closer toward the spoon end. Okay, so when we talk about a bottom-heavy object, I've got this mostly empty ketchup bottle. So, there's the mass of, it's hard to see. Okay, so it's hard to see, but the ketchup is about splashed everywhere, but the ketchup is actually really mostly empty here. So if this ketchup bottle was full, the center of mass would probably be about here, okay? So when you look at the amount of ketchup above and below, center mass would probably be about here. When the ketchup is way low, my center of mass is probably way down because you've got the mass of the bottle and then the mass of the ketchup. So the bottle's here. So for example, this mostly empty ketchup bottle, the center of mass is much lower. I wish I had a full ketchup bottle, but I don't. So here I'm going to use the salad dressing bottle. This is full. So the center of mass for this guy, for the salad dressing, is probably more like about here. Much higher up because it's got all this stuff on top and below. This mostly has stuff on the bottom, so this guy's center of mass is much, much lower. So that's, or center of gravity is what they call it. So to find the center, so for example, I could get a cup or a, can you fill this up for me? So I've got these two identical cups and they each have a certain amount of mass. And if this cup, I'd say, okay, is the empty cup, I'm guessing the center of mass, I could figure out. Okay, if I put a little bit of water in this cup and I put a lot of water in this cup, the center of mass for the cup that is filled up, well, there's more stuff above and below, so I'd put the center of mass somewhere like right in the middle. Or if this cup was only a little bit filled up, the center of mass is near the bottom. Okay, so you can find the center of mass by any object, even weird objects, if you suspend it in the air, okay, and you draw a line straight up and down. And then you suspend it, so put a rope around it, suspend it in the air by a different line, and then you draw a line up and down. And where those two lines cross, that'll show you the center of mass. Because when you're hanging something by a single point, it will naturally find its balance point. So you just find the balance point in multiple directions, you draw a line, and you find out where they cross. That is the very center, the center of mass. Okay, so if you're balancing a rock, this is when you see those people stacking rocks, they're finding that balance point for each rock and doing those, crazy little rock piles. If you take a banana and balance it, or a yardstick, you can guess, 36-inch yardstick will probably balance somewhere around the 18. Jenny, can you grab me a sharp pencil? But I want you to grab me a yardstick and a sharp pencil and 2 potatoes.
Where's the yardstick?
It's in my room. A yardstick, a sharp pencil, and 2 potatoes. Thank you. So here's a banana. So we could find, so the center of mass for the banana, so I'm gonna try to find where the center of mass is on this banana. Okay, somewhere right around here, but okay, here we go. Okay, so I'm gonna draw a line. The center of mass for this banana is somewhere around here, okay? Right. Let's see, because I could balance it. There we go. See, that's the line there. Now if I want to find out, so I'm going to hang it this way, and I can draw, is that even, okay, so, interesting. So now I'm going to draw a line, straight down from my hand. This tells me the center of mass for this banana. The center of mass for this banana is right about here. And that makes sense if you look at this banana. Why? Because why is it over here and not here? Well, if you look, it's because if you average, okay, averaging out up and down, that's pretty simple to see. It's about halfway down the banana. But if you average out where the mass is on this side and this side, well, this little guy is sticking out, right? He's sticking out here. So it makes sense that why it's so close to the inside of the banana, because you've got matter on this side, you've got matter on this side. So it's right about there for this banana. Okay, so next we're going to have, now the center of mass, that's sort of like that is the thing that stays the same. If I throw this banana in a beautiful parabolic, or if you ever see someone throw a baseball bat, and it's, I don't know if you can see that, it's spinning. Like if you see someone throwing a baseball bat, if you look, there's a nice little handy dandy illustration in your book. If you throw a baseball bat and it's like spinning through the air as you're throwing it, the center of mass of that baseball bat, or the cat, if you throw a cat in the air, same thing. So you throw a cat or a baseball bat in the air and you see it, say like this baseball bat is sort of spinning.
Draw the cat.
Spinning as it's going, okay? Sorry, that's a really ugly baseball bat. Okay, but if you look at that baseball bat, if you took slow motion photography of it, or like a, you could slow it down and see, you would see that the center of mass of the baseball bat is actually tracing a beautiful little parabolic curve. So it looks, okay, I didn't do a good job of that. So it looks like a hot mess spinning around, but the center, it's spinning around its center of mass. When you just throw anything, it spins around its center of mass. There's a really cool illustration in your book of what happens when someone's throwing a wrench, and they do it in slow motion, and they mark on the wrench a bright red dot where the center of mass is. And you'll see that is smoothly moving along a parabolic curve. Even though it looks like a hot mess, it's actually it's spinning around that center of mass. Okay.
I couldn't find the yardstick, Mom.
That's okay. Okay, so how do you topple something? When do things fall over? Things fall over when you can get that center of mass to tip over the base. Okay? So toppling an object is when the center of mass tips over its base. So for example here we've got this brick. Center of mass is right here. This is its base, okay? Got another brick. This is a much thinner brick, okay? Center mass is right here. I like making centers of mass red. Just looks cooler. Okay, so this is the center of mass, okay, for these bricks. And then I'm going to have a funny shaped brick. Okay, nice little flat bottom. It's a funny shaped brick. Okay? Looking at these, you say, which is the easiest to topple? And you'll know it's this one. Why? Because for something to be toppled, this is the base, okay? Okay, let me draw. I'm going to draw dashed lines to show you this is where the base of this thing is. Okay? This is the base.
All you need to do is get the red dot out of the...
If you can get the red dot over the base of an object, it will topple.
This will be the hardest to topple.
This is the widest base, so it's the hardest to topple. Because in order to tip this thing and get it to topple, you've got to move it, topple it such that, I'm not drawing this very well. You've got to topple it such that the center of gravity, see it's still over the base. Sorry, it's not very square. Okay, now I'm going to try toppling it more. Okay. Okay, now I think I can finally get it to fall because I got the center of gravity. So if you could see, I got the center of gravity to go past that base. Once the center of gravity goes over the base, it falls. Okay? So here, you see I only have to push it a little bit. I've got this block moving. And because the base is smaller, I have trouble drawing today. Because the base is smaller, to get that center of gravity to move out over the base and then tip over takes less work. Now with a top-heavy object, I didn't even draw the center of mass correctly, it's probably up higher. The top-heavy object like this, you don't actually have to tip very much to get it tip over. And you'll see that. Sorry, Jenny, let me see.
What?
Hold on. Okay, so I have drawn a little red dot to where I believe the center of mass to be on this guy. And you can see it's pretty high up and he's got a very small base. So you can see that I just can give it a little push and he goes down. Because it doesn't take much to get that little center of mass to tip over the base and then down it goes. You can see here, this guy's center of mass is lower because he's not so top heavy. See, this guy's center of mass was much higher. This guy's center of mass is much lower, so he's not as top heavy. And I have to give it a lot more of a push to get that red dot, you see, to go over the base. See, this is the base here. And I've got to tip it quite a bit more. Oh, okay. See, if I tip it a little bit, it'll go back to its base. I've got to tip it quite a bit more to make it go down. See, I had to tip it to where, when you have a straight line, sorry, I'm wiggling the camera. I had to tip it to where the red dot goes over where that base is, and then it can go down. Okay. Is that possible? Okay. So this is when you knock somebody over. When someone is standing, they have a bait. That's why one of the first things you learn in any sort of fighting is they say keep a wide stance. When you keep a wide stance, you don't want to be like this thing. You don't want to keep, if your feet are close to each other, your base is quite narrow. It's easy to knock you over. If your feet are far apart, your base is quite wide. It's a lot harder to knock you over. And so that's why they say keep a wide and low stance.
My guess is if you were playing football, would be a wise idea to try to grab the other guy's feet out from under him.
Well, that's one way. That's one way. When you grab one of his foot out from under him, you turn his base from being very wide to being not the same, right? A lot less. So you might say, why do things lean and not fall? Why is the Leaning Tower of Pisa not the fallen Tower of Pisa? The reason is because the Leaning Tower, way too leaning, the Leaning Tower of Pisa, the famous Leaning Tower of Pisa, its center of mass, it's right here, has still yet to go over its base. Okay, so its center of mass is still over its base, and that's why it's leaning.
But
and
how
not
did it
falling.
get leaning?
Its foundation wasn't good.
Will it fall one day?
I don't know. It depends if it's stopped, if it's just gonna hang out there, or if it's still leaning. I think it stopped moving, so anyways. So a monkey, this is why monkeys can reach much farther than a human can in proportion to like the arms and the body, is that when a monkey is leaning over to grab something, so when a human being is reaching over to grab something, when you start leaning to grab something, when you're leaning, as you put your arms out, your center of mass moves forward, and you're trying to keep your center of mass still over your feet, okay? As you lean, your center of mass moves forward. When a monkey is doing this, he can lean even more forward than the human. Smaller than the human though. Why? Because he's got a tail. And he can use his tail, he sticks his, if you watch a monkey and it's leaning for something, it will stick its tail out. Why? It's redistributing its mass behind it so it can lean out farther. So that's why monkeys are so good at climbing trees and all that, is they can use their tails to help them redistribute where their center of mass is. Back to people's center of gravity, so people don't topple. So try to reach down and touch your toes, okay? If you reach down, you can reach down and touch your toes without falling over. So this is our human being. He's gonna reach out and touch his toes, okay? So here he is, reaching out. Sorry, those proportions are all off. So here is his feet, and he's reaching out with his hands and touching his toes. And he doesn't fall over. And why is that? Well, it's because his rear goes back behind him.
His bum?
His bum goes out back behind him so that he's keeping his center of, when you're touching your toes, your base is quite small because you got your feet right there together, But he's rearranging his mass by sticking his bum out and keeping his center of gravity over there. That's why if you are backed up against a wall, you cannot touch your toes without falling over. Because if you try to do that, now you've got this guy and he's backed against a wall, his bum is against the wall, his feet are here, and now he's trying to reach down and touch his toes. His center of mass, so this is his base, okay? His center of mass, you can't do it, go ahead and try. His center of mass, yes, since you just hit the floor, his center of mass cannot remain over his base because he can't stick himself out in the back. It's like if you chop a monkey's tail off, it's going to have much harder time.
So don't do that to monkeys.
Right. And squirrels too. Squirrels use their tails to help them. Climbing creatures, God gave them tails.
Well, if you bend your knees, you can do it. Mom, if you bend your knees.
So, I guess theoretically, if humans wanted to be really good at climbing things, you could probably make some sort of contraption, some robotic contraption that you were like, all right, now stick out this way and whatnot. Anyway. Okay, we did the tipping. Okay, so now we're going to talk about stable and unstable equilibrium. Stable and unstable equilibrium. So equilibrium is when something isn't falling over. Okay?
Wait, but monkeys can't sit, right?
Shh. I can sit.
Then how do they not squash their tail?
They figure it out. Okay, so stability. So now we're going to talk about stability. Stability. So unstable equilibrium is when something is stable, but you touch it and it falls over. So think like those artsy rock piles, okay? Unstable equilibrium is when something is not falling, is not toppling, equilibrium, but if you touch it, it will fall, okay? Then there's stable equilibrium. That's, you can touch it and it'll kind of center back. It will not fall over. And there's actually a very precise definition between these. So unstable equilibrium, let's say we've got that cone again, and we've balanced it on its tippy top, okay? Stable equilibrium, we've got the cone resting on its bottom, okay? So here, we'll say, remember with the cone, the center mass is going to be closer to the fat end. So the center mass is here, okay? So stable equilibrium, its base is that little tip of the cone. Its base is right here, okay? So it's lined up over it, it's not. You touch it, and what happens? You touch the top of that cone, and what happens? The center of mass goes down. As soon as the center of mass goes down, as you touch it,
Even slightly,
any direction it goes, it will go down. See? Moves this way. And as soon as it's down, look, it's no longer on the base, and bam. But you notice that that balanced cone, any direction you push it from, that center of mass is going to go down. And down, down, down. Any way you push it from, that center mass is go down. This is how we define unstable equilibrium. If you touch it and the center mass goes down, it's going to fall over. Now, stable equilibrium, remember it's close to its about here. Stable equilibrium, you notice, okay, if I'm going to try to tip this cone over and I push it, what happens? Any direction that I push it in, so I'm going to, here, imagine I push it that direction. Any direction I push it in, it goes up. The center of mass is actually going up before it goes down, right? If I keep pushing that cone, eventually I will get that center mass to go down, and it'll be over its base and will hit the floor. But I've got to push it quite some ways. I have to push that center mass up before it goes down. The same is true for a can. Remember our can example? If I push this, you'll notice I'm actually pushing that center mass up because it's pivoting over the corner of the can there. So that's why it just goes back to stable equilibrium. This is stable equilibrium. It keeps going back. Now I can get it to topple if I keep push until finally that center of mass is coming down again. But in order to get something in stable equilibrium to topple, you've got to push it enough that that center mass goes up and then comes down. And as soon as it starts coming down, you know the thing's going to topple. So the definition for unstable equilibrium is when touching it will make its center of mass go down. The definition for stable equilibrium is when pushing it or touching it will have to make it go up first before it can go down. And the definition for neutral equilibrium is, okay, say we've got the can on the side. Center mass is the same height, no matter how much I push it. So the can on its side would be an example of neutral equilibrium.
You can't knock it down because it is down.
I mean, I could try to do that. I don't know.
But then that goes up.
Yes, then it would go up, you're right. But neutral equilibrium, you'll see, is that even if I touch it, it's just staying. Stable equilibrium, the difference in neutral and stable is that stable, it's going up when I touch it, see? And so it wants to go back to equilibrium. Unstable equilibrium, that center mass will go down when I touch it.
Because when you make it go up, it wants to go back down on the closest route, and so we'll go
exactly
that way.
So you have to tip it enough that the closest route for going back down is over the edge. Okay, so that's what the difference is stable and unstable equilibrium. And this is why the balancing a pencil on your finger is quite difficult for me, because I'm not good at this sort of thing. There's some other kids I knew who were really good at it. Okay, so there we go. So I balanced that. See, so the mass on this side is equal to the mass on that side. Looks like that little eraser must be pretty heavy to balance that much wood on that side. Well, anyways, you see, I've got this in. This is in unstable equilibrium because I touch it and the whole thing falls. Because the center of mass of this pencil was directly over my finger, and any way you go, it goes down. Now, I'm going to take potatoes.
I can make it not go down.
Is it still recording? Just make sure it's still recording.
Yeah.
Okay, good.
Can I show you?
Wait, hold on. Shh, I'm doing the potato trick. Hold on.
Down?
Shh.
What are you doing?
I'm doing the potato trick. So now, now I've got potatoes on either end of my pencil, and it's actually way easier to balance it. This is so much easier to balance with two potatoes on the ends. And the reason is that now the center of mass, depending where I've stabbed it into the pencils, see, now I can wiggle it and it's in stable equilibrium. Did you see that? I wiggled it instead of just falling off my finger. And the reason is because now that I've added the potatoes, the center of mass, and I think I tried to stab more to the top of the potatoes. It's a little hard to see. Maybe I should make that a little more exaggerated. Okay, let's do that a little more exaggerated. I'm going to stab here. Now the mass of the system, hold on. Now the mass of the system with these potatoes is actually under my finger. And now that the mass of the system is under my finger, Because look, think about it, okay? What is the center of mass of this, okay? So you've got it this way. Because of the mass of this potato and that potato, the center of mass is actually under my finger, right? Because we know it goes this direction, but look, when you see how much matter is below my finger versus above my finger, like the center of mass is gonna be right about here. So now that the center of mass is here, when I touch that and I tip my potato, see, it's stable equilibrium. They try to keep going back to equilibrium. Why? Because the center of mass, imagine a little red dot here, you know, if I tip it this way, it has to go up. Do you remember how if me touching it makes the center mass move up before it can fall over, it's stable equilibrium. So now that I've got it like this, you know, I can do this. Okay, that slipped on my finger. Got potato liquid on my finger. Now I've got this, like the center of mass, it was about here, it has to go up. It has to go up. And so this is stable equilibrium. That's how you can touch this and it will balance. Remember how much trouble I had with the pencil by itself. So this is actually much easier to balance than the other guy. Okay. Center of gravity. People's center of gravity, not toppling. This is hugely important in sports and in warfare.
So is this a one-handed sword or a two-handed sword?
It depends how big you are. A man could maybe fight with one hand with that. A woman, two hands.
I can't fight. I can like.
Okay, so back to
I can hold it up with one hand.
Yeah, if you'll notice in Lord of the Rings, when Eowyn is fighting with a sword, she's fighting two-handed on a sword that Aragorn would fight one-handed with. I think if you look.
But I couldn't fight like this.
Okay, so back. Let me finish. Okay, so people's center of gravity. The cool thing is that people's center of gravity, when you're walking, you actually are intentionally falling. When someone is walking, you are intentionally moving your center of gravity till you start to fall, and then you catch yourself with your foot. And then you pick up your other foot, and then you start to, what happened? And then you start to
so
fall.
hard for 2-year-old, or not 2-year-old?
When kids are learning how to walk, you're learning to move your center of gravity till you start to fall, and then you catch yourself with your foot. Then you start to fall and catch yourself with your foot. Pigeons do the opposite. Pigeons, if you ever watched a pigeon strut, as a little pigeon will put its foot out and then move itself. But humans don't walk like pigeons. We walk, we let ourselves fall, and then we catch ourselves. So it's a way that we are using gravity to help us move ourselves along.
Wait, so pigeons walk like this?
Yeah, watch a pigeon walk. It's interesting. So, humans, so we use our center of gravity in many ways. Like we were saying, why do they say wide and low stance in a fight? Well, you don't want to topple. You don't want the enemy to topple you. So you take a wide stance, so you have a wide base, so it's harder for them. And you want to be low to the ground. Why? Because if you're lower to the ground, your center of mass is lower to the ground. The lower your center of mass is, the harder it is to topple. You know, it's easier to topple top heavy things, right? It's easier to topple top heavy things versus bottom heavy things. So that's why they, in fighting, guys will get down wide and low. Okay, and... oh, another interesting center of gravity thing is you will see, like we had with the potatoes, if you see places where women still have to haul heavy things long distances, so like in Africa where they're bringing water, a lot of times they'll put the water on their head because they're lining up the center of gravity of that bucket right along the line of their body. That just makes it easier than if you're trying to hold it on one side. So then you're having to readjust where your center of gravity plus you and the bucket are.
And it still is much easier for me.
Another way that you'll see a woman transporting huge amounts of water was like the potatoes. This is, I think, the best way is that you have, or like those old-fashioned, like you see pictures of like milk girls that had to bring in milk from the milking places, is that they would take a yoke, and you're holding the yoke, and you've got a bucket on either side. And I think I saw, and it balances. So you're not having to fight it this way. I mean, you still get the weight of it, but it self-balances like the two potatoes. So I think I saw a really cool picture of this lady. It was during some refugee evacuation, and she's holding one of those things with the yoke with the two buckets, and she's got her kid in one, and she's got like a 50-pound bag of rice in the other. She had to move rice and her kid, and she just figured, okay, this way it balances. Okay, gymnastics and ice skating. If you watch any gymnastics or ice skating, it's all about their center of gravity. Like all those twists, flips, turns, leaps over the bar. They're doing look what they're doing. Yeah, look what they're doing. Bottle flipping, very popular among kids. Elementary school children. It's all about trying to flip it just right so the center of mass will land over that little base. Gymnastics, ice skating, all about center of mass, rotational mechanics, etc. So next time you watch sport like pole vaulting or when they do those spins, or ice skating when they're doing the spins or whatever, watch what they're doing with their center of mass, because most of sports is all about moving your center of mass. All right, that's the end of that lecture, chapter 10 on center of mass or center of gravity. It's the same thing. Can you stop the video?
Okay.
Sorry.
Bye. Have a good day.
All right, here. Okay.